are just sleeping late and they're not stuck somewhere in the mountains. Flo, do we have things to announce? So, in the break after Giulio's lecture, we will do the COVID testing again. So let's hope that this time everybody will be negative and we can act accordingly. Another note is that yesterday dinner, there were 4 tables missing and only about 1 table worth of people said that they will be missing. So the cook was not happy because they cook for you and then they throw away the food. So next time make sure if you are not going for dinner that you tell them. And if that will happen again, I will have to go around and take the names of the people who are there so that I have the names of the people who are not there, and then somehow, I don't know what I will do, but please make sure that you tell them. You don't want to food for you and throw it away, right? That's just silly. Something else we should say?
Drawings.
T-shirts, go on.
Okay, so I am announcing a T-shirt competition. So if anyone has a nice idea for a fun drawing to put on a T-shirt or a mug or a bezouche, you have 5 days. So we will open a channel on Slack and try to be creative. And at the end, we will find let's fuse the design and make a T-shirt and a mug for all participants. So, okay, come on, show me what you got.
Take advantage of it, because they used to have goodies.
Alors, j'enlève toujours là. Ou ça?
From what I understood, they don't anymore, so let's make our own. And we pay for it, so we just need your creativity to make it happen. And with that, without further ado, let's go on with the next lecture of Giulio. I'm looking forward to hear about the cat's rice and the landscapes and all that.
All right, so indeed, what I would like to do today is to show you a method to compute the number of critical points in high-dimensional landscape. So we discussed already, so while in machine learning estimation problem and also in physics of disorder system, there are high-dimensional rough landscape, and it's very interesting to try to know their structure. They cannot give you then all the information you would like to know what the dynamics is going to do, but at least they give you some information. And well, discussing with some of you, I know that you are interested in this kind of question, for example, in deep networks or in estimation. So, well, it's a method that allows you to get, to indeed, at least in some cases, to get all the information you want to know about the property of the landscape. Then at the end, I will tell you what is the frontier, meaning what we can do also in cases which are more close to neural networks. So the kind of landscape or energy function that I'm going to study is this one, and then let me define it, and then I will motivate. So it's an energy function which depends on variable SI. So the variable SI are like in my previous lecture when we define on the sphere, n-dimensional sphere. And then this I will define it in a general way. It's the minus the sum over p prime from 1 to infinity of C of p prime. And then you have sum over I1 IP, JI1 IP, SI1 SIP, where J is, like in my previous lecture, are IID random variable, 1 over 2 and p minus 1. And I here goes from all the index I goes from 1 to n. And then I will add also second term, which is minus r. And then I have sum over, I call it p second, from 1 to infinity. And then I will put b of p second divided by p second. Then I have n here, and then I have sum over isi dot vi to the p second. Okay, so it's a generalization of, sorry?
You want the p to be p prime in the first equation?
Yes, it did. Thank you. Okay, so actually I already did several, let's say, misprint on the board in the previous lecture, and now they are all going to become more. So please stay with me and correct me. It's increasing. Tomorrow will be worse. Okay, so the idea is that you have 2 terms, exactly like we discussed last time. There is one term which is, it's a random term, so you have a random part in the energy. And then this term, what it represents is instead a deterministic part. And you would like to understand what is the interplay between these two and how, if R plays the role of the signal-to-noise ratio, and how actually, if R is larger, this one is going to win about the on the other, and how this depends on the form that you have here and there. So just to give you examples, so I mean, this is very general. So example of, so number one will be tensor PCA, which is so it's a model, a statistical model of tensor PCA that was introduced by Andrea in, I think, 2014. And so this corresponds to the case in which you just take one term here, let's say P prime, just one term here. P prime here, P prime equal to P second equal to P, and it will be larger or equal than 3. Okay, so you have just one term in this sum. You have just one term in this sum. And so this case is very similar to what we discussed last time, but it's generalization. If you remember, last time we said if you have a vector V, and from this vector V you construct a matrix Mi1, I2, in which you have this vector, and then you have a term, which is the noise, Ji1, I2. This is what we studied last time, and then we study actually the simple landscape of this problem, which you have just 2 critical points, and we look at the dynamics. Well, you can do a tensor generalization of this, which you have, for example, I1, I2, I3, and then you get Vi1, Vi2, Vi3, plus lambda, J, I1, I2, I3. And so then if you define, as we did last time, an energy, which is T, I1, I2, I3 minus S, I1, Si2, Si3, square, sum over I1, I2, I3. Then exactly like the procedure that we did last time, where you take the square. So the square of this does not depend on S. The square of this does not depend on S either, because you have the spherical constraint. So when you develop, you sum, it goes away. And so there is only the cross product. And in the cross product, in T, you have this term and this term. And so you reconstruct, indeed, this term here with just one, with P equal to 3, and this term here with P equal to 3. Okay? So this is an estimation, is an example of this energy function for an estimation problem. Yes?
What is Vi in the cell?
Sorry?
What is Vi in the second cell?
What is this?
Vi.
Vi, sorry. So Vi is a vector that you want to retrieve. So Vi is, let's say it's a vector, you can think it's a signal. It's exactly like the same sectin than before, and it's defined sum over IBI. It's also defined on the sphere. Okay, so this is one example. So just the generalization of what we did last time. Questions?
What was the first thing you pointed to, just after the sum, for the capital N?
This one?
Yes.
Is
Just before the N.
this one?
Yeah.
It's just a coefficient, just to define. It's B, P second. It's just a bunch of numbers. This one and this one, they define the energy. Okay. Then there is another actually way to look at this problem, is that what we are studying random Gaussian function on the sphere. On the sphere in n dimension and n go to infinity. So how we can see that we are studying random Gaussian function on the sphere? So let's consider for a moment, just an example, just one term, one single term of this. Let's say E of S, which is equal to minus sum over I1 IP, J I1 IP, S I1 SIP. Okay? So this is a function on the sphere. And it's random because these J are random. Okay, now we can study its average value and its, so you see, well, first thing is a random function, and also you see it's a Gaussian random function because you are summing a bunch of Gaussian, so it's going to be a Gaussian function. Do you agree? I mean, the sum of Gaussian is a Gaussian, so it will be a Gaussian. So this is already, you know, it's a Gaussian function. And we can compute, so you know that a Gaussian, the only thing that you have to know is its mean and its average. And so we are going to compute the mean. So today, I'm sorry, I'm not going to use the expectation since Remy say that he doesn't do it, so I will not do it either. So this is the average or the expectation, so E of S. So the average is simple. Well, if you take the average over the J, well, here, since the J have zero average, this will be zero. And then you can compute the covariance, E of S, E of S prime. And so this will be sum over I1 IP, J I1 IP, SI1 SIP, sum over, let's say, I1 P prime, I prime P, J I prime 1, I prime P, S prime, S prime, I prime P, average. Now the J are IID random variable. So in this average, you have to couple them, otherwise you get 0. And so from this, you're going to get the sum over I1 IP of 1 over 2 NP minus 1 SI1 S prime I1 SIP S prime IP. And then you have the sum. Well, so this sum, you can put it here, like this. Sorry, let me write to NP minus 1. So you can put the sum here, I1, then sum IP. And so this is nothing else than n divided by 2, sum over I of Si S prime I divided by n, which is what I think has been discussed already, is the overlap between the configuration S and the configuration S prime, and this is to the power P here. Okay. So just to say that, so the covariance of this Gaussian energy function is going to be equal to big N divided by 2, and then the overlap on the sphere between the two configurations. Okay, so this is, well, it's a way, so if you, now we can forget, if you want, about the J, and you see that what with just one term, what we are studying is a Gaussian random function such that the average is 0, and its covariance on the sphere is related to, well, the overlap to the power P. So now if I take my first example, so, ouch. So if I take everything together, so where can I put it? Well. All right, I will erase it here. So now we have that I continue, always 2. So now the Gaussian random function that we are going to study is a generic type of Gaussian random function on the sphere, such that the average of E of S, now, if I consider this, the average, you see you have this term, which average to 0, but then you have this term, which is fixed, is deterministic. So this is going to be equal, so minus R, and then I will write in this way, F of D of Q S V, where Fd of x, so it's a deterministic function, which is just defined like sum over p second from 1 to infinity of b of p second divided by p second. Sorry, here there was an n in front of x to the p second. Okay, so I mean, what I'm saying is that the average of E, so this is a Gaussian random function, is going to be equal to minus R. So R is the strength of the deterministic part, and then a certain function which I define here. So it's well, if you fix, depending how you fix the b of p seconds, this would be a specific function, and it's a function of the overlap between S and a specific vector v, which will be, I mean, our signal. Okay, so it means that here, if I look around the sphere, well, around the sphere, this deterministic part is very simple. It's just a function of, well, the overlap between S here and V. So this is not, it's a very smooth dependence on when you move S on the sphere. And then there is the E of S prime minus, so the covariance P of S prime. And this is going to be equal to, again, this, since E of S is a random Gaussian function, you just have to know the average and the covariance, and this is going to be equal to sum over, to, let me define this way, to n divided by 2, a function f of r of q s, s prime, where actually f r of x is equal to sum over p prime from 1 to infinity, or of c of p prime square, and that's it, x to the p prime. Okay? So this is just to tell you that I could have actually, instead of define the energy function this way, I could have just say what we are going to study are Gaussian random function on the sphere, which is they have a certain average, which means that the average is preferring actually S. We are going to study a case in which the function is defined in such a way that S likes to be close to V. But then on top of it, there is a random part, and this random part has a zero mean, and then a covariance, which depends actually on the overlap between S of S prime. So naively, if I have to draw in a way which is very sketchy, you could think that you have a kind of, let's say, I don't know if you understand what I mean, but you have, let's say, something which is going to be, well, not like this. It's going to be rough, and then it's going to go down here if R is large enough. This is the idea. Okay, so you really have, on the sphere, you have a random part, and then you have a part instead that tells to S that wants to be close to V. And what you want to study is, okay, how many critical points you have, how they are structured along the sphere, and especially what's going to happen when R change, when R is large or when R is small, and how this depends actually on this function, on this function fd, which is the deterministic part, and fr, which is the random part. Is the problem clear? Yes? Okay. So let's go now. So the idea is similar to what we did on Friday, but now it's more complicated. So if you remember, on Friday we had defined the energy function, then we studied the critical points, and then we studied the dynamics. So here I want to do the same, but today, it's more complicated. So today we're going to study all the critical points. And in order to study the critical points, I will introduce a method that I think it can be useful. If you are looking at different problems in estimation and also in neural network, even though this is really the frontier of what we are able to do. Okay, so if there are no questions, I will start with what is the method to study the critical point in this case. And we are going to see that in this case, you can have an exponential number in the dimension of critical points. So really, here, the landscape is going to be very, very rough. Okay, let's start. So maybe I have to say also that this kind of this kind of function, if you don't have the deterministic part, are functions that arise and appear in the problem of spin glasses and glasses, which I think Mark told you about already last week. And indeed, there have been methods that have been developed to understand the landscape using first replica, and then there have been methods that have been developed before the method that I discussed today to understand the number of critical points. Okay, so now what I want to do is to discuss the method to study the number of critical points. And this method is called now Katz-Rice method. And so what we want to do is to study the number of critical points of E of S on the sphere. And so what we want to study is to study how many S we have, how many S we have, such that the gradient on the sphere of E of S is equal to 0. So I will put this orthogonal to remind you that I am going to compute the gradient on the sphere. So it's the gradient along the sphere. that has to be 0 to study the critical point. So in order to do this, we are going to use an equation which is so if you want to study, if you have a function, let's say f of x in one dimension, and you want to study how many 0 does it have, so here we want to study the 0 of the gradient, then what you can do, you can use a formula which is integral over dx, the delta function of f of x, and then you have f prime of x, which is the Jacobian. Okay. This is in one dimension. Now in n dimension, the generalization of this in n dimension for our case is going to be that the number, so we'll denote this, the number of critical points between energy E and energy E plus dE. So it's the number of critical points with energy between E and E plus dE is going to be equal to the integral over ds of delta. So this is the n minus 1 delta function of gradient of E. Then you have the equivalent of this, which is the absolute value of the determinant of, I will write in this way, this is the Hessian, E of S, and this is the Hessian on the sphere. And then I also add the requirement that E of S is equal to E. Okay, it's between E and E plus D. Okay, that's the, exactly, it's the generalization of the one-dimensional expression.
Is it gradient of f is again for one-dimensional?
Sorry?
So for one-dimensional fx, is it gradient of f? When we see the equation above.
Here? Yeah, because it was in one dimension.
Oh, I was wondering if you said delta is it gradient of f.
Did I did something
because
wrong?
It's looking in one dimension, it's looking at
Yeah.
0 of f.
Yeah,
So
sorry.
You wrote down the formula in 1D for the number of zeros rather than
Yeah.
critical.
Ah, okay, now I understand. Yeah, sorry. So it's indeed. Okay, yeah, I should. Okay. Okay, so, all right, so we should compute this. Now, this is called Katz-Rice formula, from what I understand, because, well, if you want to define it correctly, I mean, if you want to show that it has a meaning, when E is a Gaussian random function, it's not, I mean, it takes some work mathematically, and this Katz-Rice, they did it. So this is why it's called Katz-Rice. I mean, for physicists that don't, let's say, worry too much, indeed, it's just a generalization of this one. So now the important thing is to think about is that this is the number of critical points with energy between E and E plus D. It's a random variable, because here what we have inside, so we have a Gaussian random function. So this means that we have to decide, well, it's, if you want to do a computation, what we are going to compute. And what we are going to compute today, it's the average. Okay, so we'll take the average of this, which means that I will take the average of this. And now the average, this average of the number of critical points, this average is called, and I think it was already discussed, it's called a Nilde average. And the reason is that this number, you expect that this number is going to be exponential. It's going to go like exponential in n, the number of dimension, and then a function, which is of order 1, of the energy, or more correctly, the energy divided by n. Okay? Now, when you have a problem like this, which is the classical problem in disorder system, well, you know that, well, what you would like to compute in reality is not this, but you would like to compute the log of n of E. And why? So this is called quenched. Why you want to compute this? Because if you take a typical realization of this Gaussian random function, the variable, which is the number of critical points, typically will behave like exponential of n, the average of log n of E. No, well, without the n. Okay, so this is really, I mean, in a typical case, what you would like to have. but it's much more complicated, and it requires at least, well, I will discuss later in which case you can really do it. But okay, we are going today just to see how is the method. We are going to compute the annealed one. In some cases, I mean, the annealed one gives you already several interesting information. Okay, so this is what we are going to compute today. Questions?
Can I just ask a conceptual question?
Yeah.
So I mean, suppose you could compute with the average and let's say the variance for the number of critical points. Is that good enough for your purposes, or do you really want the full expectation of the log?
So it depends. So in some cases, if you are able to compute the average in the variance, if I'm correct, then in some cases you can prove that the quench and the annealed are the same. But if they are not the same, then the average doesn't help you too much. But
that was done in one case. That
yeah.
is, pure PSP model.
Yeah. Yes, I will give a set of reference at the end. So indeed, in some cases you compute the two. I mean, if you know how to compute the average, in principle, you know how to compute the variance. It's a bit more complicated, but you can do it. Then whether this is useful, it depends on the case. Some cases it's useful because it proves that annealed is equal to quench. But if quench is not equal to annealed, then no. Then what you have to do is you have to use replica or something else. But it's in order to try to compute this quantity. Yes. So Marco didn't explain annealed and quench. No. So this comes from physics, actually, because in physics, the J, so the randomness. Okay, I think Mark told you about the spin glasses in which you have magnetic couplings, which are frozen, and then you have spins that interact. So what you can think is that if you study the dynamics of this system, if there are two possible cases. There is one case in which the J are really random variable that you don't touch, and then there are the spins S which are moving. And so this is the quench case, and quench really comes from physics. You think that there are some frozen part, and the other ones is moving. Or you can think that the couplings are also moving. So in this way, this is annealed in the sense that they move in together with the other ones. So and so in this case, you see I'm doing well, if I computed a partition function, I would do so here I'm not computing a partition function, but in physics, when you compute a partition function, you do an average over the degrees of freedom, let's say the spin, and the coupling at the same time. Whereas instead here in this case, you have your system in which the variables, the randomness is frozen. So it comes from physics, just to say. So not sure that it helps much in this case, but it comes from physics. I can tell you more concrete example later. Yeah.
Shouldn't we pay specific attention to the minima?
Yes. So I will tell you later how to do the computation for minima and to a fixed index of the critical points. But for the moment, I just do this, which is the easiest thing to do. Then I will tell you all the generalization. I will tell you as much as we can generalize and as much as we know. So, but for the moment, I just stick to the simplest case. Other questions? Okay, so let's start. So how do we compute this thing? So this can be done actually, it's not so difficult. It can be done in more or less 3 rather easy steps. Okay, so maybe I should also say that the first kind of computation in the way I'm discussing was done by, so I will give you the complete list of reference, but just to say who was the first to do it in this case was Jan Fyodorov in 2004. And then there is a long list of following paper that I will discuss with you, but he was really the first one. Okay, so Okay, let's say 3 rather easy steps. Okay, step number 1. So here we have to compute this average. So while we can, of course, take the average inside. And then we can ask, what is this thing here? What is improbability? What is it? What we are without the DE? Let me keep away the DE. So what we are computing this way, so we have n of E, which is equal to the integral over ds of something which is P of S. And what is this P of S, which depends on, well, many things, but what is this P of S? Yeah. Yes, it's the probability density of having a critical point with energy E in at S. Okay, sorry, I put the vector. It's a physicist sin. All right, so now what is the first step is that, okay, this P of S, how is it? So what we know is that, you remember, when we compute the Gaussian random function on the sphere, we saw that statistically, the covariance only depends, maybe something that I should say also is try rather easy step, and we are going to consider the case in which f deterministic is equal to 0. Okay, it's just to be simple. Then I will tell you the results at the end when we put this back. But otherwise, it will take it will be too difficult and too long. And I want just to give you the 3 main ideas, and then you can generalize as much as you want. So in this case, what we have that the average of E is equal to 0, and E and the covariance or the variance, yes, E of S prime, was equal to n divided by 2 FR of Q of SS prime. So the statistically, you see, since this depends just on the overlap, which is the related to the scalar product between S of S prime, you have translation invariance. Sorry, translation invariance on the sphere means rotation invariance. Which means that, what do we know about this P of S? It's uniform, yes, because, it has if we have rotation invariance on the sphere, then the probability that S is in a specific direction is a critical point will not depend on the direction. So we will have that actually P of S is equal, let's say, of P, for example, let's say P1, where 1 is just, one specific vector, for any S. Which means that this I can just write it like P of 1, and then the integral over ds. And this is nothing else than the surface of the sphere in n dimension, a surface of a sphere of radius square root of n in n dimension. So this would be P1, and then the surface, let's say, of the sphere in n dimension of radius square root of n. That can be, it's easy, it's known exactly, it can be computed, and I will give you the formula later, or you can do it as an exercise. So this way we know that, first step, it's simple because, we have just to compute P of 1. So the second step is how we compute P of 1. Okay, let's see what is P of 1. So P of 1 is the average of delta function of gradient on the sphere of the energy in 1. So 1 is, let's say, is the one in with all the components which are the same. And then we have the determinant on the sphere, E of 1. And then we have delta of E minus E of 1. And then the average. Now the nice thing here is that, if you now what I'm going to discuss, but maybe you see it already, let's look at what is E of 1. So E of 1, let's say in the simple case in which you have just one P. So P1, all P1s are 0 except P1 equal to P in the sum. So this E of 1 will be sum over, okay, let me take the notation. So it's, well, okay, it's sum over I1, IP. Then there is a constant in front that I will put to 1. And then I have J, I1, IP. And then in principle, well, I have 1, 1, 1, 1. So I have 1 here, okay? I mean, 1. Okay, so I will not put the 1 here because it's just 1, okay? So what is this? I mean, it's, remember, here we have to take the average over the j's. So with respect to the j are Gaussian variables, so E of 1, what is it? Gaussian, right? Now, I can do the same. I mean, it's, again, this E of 1, so the E of 1 is a Gaussian variable, but actually the gradient, it's the same thing. The gradient, I mean, I have to compute it, then I put s equal to 1. It's just a sum of bunch of Gaussian variables, so it will be Gaussian. And the Hessian, again, will be Gaussian. A Gaussian matrix is a Gaussian vector, and this is a Gaussian variable, but they're all Gaussian. And what you want to compute, it's an average over Gaussian variable. So the only thing that you have to do when you have to do average of Gaussian variable is, well, you have to look at your Gaussian variable, compute their mean, compute their covariance, and then you compute, I mean, whatever you want. So this is now what we are going to do now is to see, well, what is their mean, which is easy, and what is their variance, their covariance, and then you will see the computation simplify a lot.
Are they independent?
We are going to see now computing them. Okay. Okay, so, well, let's compute. So first, all the means, you can see since the average, we know that the mean of E is 0. It's here, it's in this case. So all those have 0 mean. You can check it. So the mean are all 0. Sorry, I'm saying something stupid here. So so the mean as Gaussian variable, the mean of E1, the mean of the Hessian, and the mean of the gradient are 0. And now we have just to compute the covariance. So let's say the covariance, for example, of E1, well, it's simple. Well, we just have it here. We take S equal 1, S prime equal 1. Then the overlap, since it's the same configuration, is 1. And so this is going to be equal to N2 divided by 2, FR of 1, where this is just a number that you can compute once you know the function. Then there are all the other terms. And I will tell you how you do the other terms with a trick, and then, but I will not do all of them. So imagine that you want to compute, for example, you want to know whether the gradient is correlated with E1. This was one of the questions, okay? How do I do this? Well, I'm going to write that this is actually the gradient. I will do the following. So I will take ES prime, average. I know that this is equal to N divided by 2, F of Q of SS prime. Then what I'm going to do, I'm going to take the gradient on the sphere of this expression. So I can do it. I take the gradient with respect to S here on the sphere. So when I take the gradient here, well, it's simple. I'm going to get F prime here, and I could get S prime here. And once I have done this, then I put S equal to S prime and equal to 1. So if I do, sorry?
The gradient of Q is S prime or S prime divided by N?
You're right. Sorry, there is no N here, I think. So let me do it. So it's, yes, it was sum over I, Si prime divided by N. So when I take the derivative with respect to Si, I get Si prime divided by N. So there is no N. Good. You're right. Thank you. Okay, so now we have the gradient E of 1 is equal to, so 1/2 f prime q1, so which is 1. And then we have 1 here. Now, remember, we have 1 is here, and we want to compute the gradient. The gradient is on the sphere, so it's orthogonal to 1. So this means that if I put components, it means that if I look at the components of this vector, I should, for example, the component alpha, this is a vector. It means that I multiply this vector by a vector which is orthogonal to 1. So this means V alpha. Since it's orthogonal to 1, I get 0. So this means that this actually is 0, okay? I don't know if I understood what I say. It's just saying that, this gradient here lives in the space which is orthogonal to 1. So, well, I can look at each component. Each component is just the scalar product with a vector which is orthogonal to 1, so you will get 1. So you will get 0. So this means that actually in this way, you know that the gradient is independent on the energy. They are not correlated. So just using this trick, you can compute all the covariance. So we are not going to do it, but you can do it. So I will just give you what they are. So we have, so the first, which is here. Then you have, then you know that gradient E of 1 is not correlated with E of 1. Then you can compute the variance of the gradient. And this is equal to, so let me put the component alpha and beta here. And so you're going to get delta alpha beta f prime of R1 divided by 2. Hope the factor n are correct. And then so now we still have to compute the Hessian. And so for the Hessian, E of 1. And so this is also a matrix with indices alpha and beta. And you can show that this is just a GOE matrix. Let's say alpha beta, if I put the indices. So this is a GOE. And then this is correlated, actually. It's not correlated with the gradient, but it's correlated with the energy. And it's correlated in the following way. It's f prime R1, E1 divided by n, delta alpha beta. And this GOE has actually a variance such that, so G square alpha beta average is equal to f second R1 divided by 2n. Okay, so this is all you need. So we have this, then we have this. Then we know that gradient is not correlated with the energy. And then we know, well, the Hessian, well, is just this GOE matrix, which is not, it's just independent of everything else. And then it's not correlated with the gradient, but is correlated with the energy through this term.
Is there a quick way to see that?
Huh?
Is there a quick way to see that?
It's, the computation was quick. No, I don't know. Quicker than the computation, I'm not sure.
The fact that the gradient and the value are independent?
No, I think that the Hessian has this correlation, so I don't know. Maybe there is.
Yeah, because if you look at a single tree, instead of hitting it with the only one vector, hit it with the first physics vector, E1, etc. Right? Hit it with E1, so look at it with E1. So this is taking the tensor and slicing the first slice of the tensor, setting all the indices equal to 1 except the first one. And this is just the matrix with independent tensors. If you take the tensor J, J, 1, 1, 1, 1, 1,
Yeah.
this is a GOE matrix.
Yeah, sure. But then there is this correlation. But yeah. Okay, so now that we have this, in principle, we have all the ingredients to compute this term. Questions before I compute? I go on. Okay, so let's continue. And let's compute this P1. Okay, so let me write the equation. Okay, so let's really write in a pedantic way what does this mean with this average. So I have to integrate over, let's just to simplify a little bit the notation, the component alpha of the gradient of E1, I will call it f of alpha, okay, just to simplify the notation. And E1 divided by big N, I will call it small e. So what I have to do here, so I have to, well, first I have to average over, well, the energy. So I have this multivariate Gaussian integral. And so let me write what it is. So I'm going to have the integral over df product over alpha from 1 to n minus 1 of df of alpha of exponential of minus f alpha square divided by 2. And then I should put the variance of the gradient, which is here, which is f prime r1 divided by 2. And then I have square root of pi fr prime 1. So these are the measure for all the gradient. Then I have exponential of minus e square divided by 2. So this is because E1, I'm writing the measure over E1. E1 is a Gaussian variable. So it's going to be minus e squared divided by n. And then I should be careful. There is an fr1 divided by 2. And then there is a big factor of n here just because I redefine e it's in this way. And then I have square root of pi fr1 divided by n, if I'm not mistaken. And then I have also the, the integral over all the Gij. Okay, I've just written the measure. Okay, so this is this is because the Gij are independent. And then I have to write all the rest. So I have the delta function, so the product over alpha of delta of f of alpha. These are all the delta functions that impose that the gradient is 0. Then I have the determinant of G minus f prime r1 small e, well, e small e. I see that I'm going to have a problem very soon. Delta, alpha beta. And then here I have delta, and since I already use e, let me do it this way. So I see I have d alpha, so here I put a dE bar. This is E bar. This is E bar. And so here I have dE minus E bar. Okay. Okay, looks ugly, but now everything is going to simplify because, well, here I have a lot of integrals, but they all get a delta function. So I can integrate over all f of alpha. I have just to put f of alpha equal to 0. And while the integral over E bar is simple because I have a delta function also. So this is going to be equal to, well, there is this term, 1 over square root of pi fr prime 1 to the power n minus 1 because I have n minus 1 term. Then I have this one, which is just exponential minus n e square divided by fr1 square root of pi fr1 divided by n. And then I have the last term, which is the integral over dGij. So it's the integral over a Gaussian, here there was a term missing. So let's say there is the Gaussian for Gij. And here I have the integral of dGij, let's say the Gaussian that I should write for gGij. And then I have the absolute value of the determinant G minus f prime of R1 Now this E bar is equal to E because there is this one, and then I have the identity here. Okay. Questions? No? It's fine? Okay, so well, this, I will just rewrite it in this way. It's just the average over the GOE matrix of the absolute value of the determinant. So here I have this term here that I computed. So now you see, I mean, these 3 steps, we compute term by term. First, we compute, there was a term that will pull out, which was the surface of the sphere in a dimension. Now we have this term, which we pulled out. So we have, the third step is to compute this one. Okay. Okay, third step. How do you compute this? So, well, you can compute it in this simple case exactly, even when n is finite, but this is not what we are going to do. In any case, we are going to study the case in which n is very, very large. And so, well, let's rewrite this, what it is. This is, well, is the product over all the eigenvalues, let's call it alpha, of this, well, the absolute value of the determinant is going to be lambda alpha. So let me write it. Yes, so it's lambda alpha are the eigenvalues of the GOE matrix G. And then, well, I have to shift them by a constant term here. And I have to take the average over the GOE. And then sorry? A prime, yes, thank you. Okay, so this, what is this? This I can always rewrite it like exponential of sum over alpha of log of absolute lambda alpha minus fr prime 1e. Which is also the average of exponential of, well, this I can rewrite it using the density of eigenvalues, d lambda, rho of lambda, with a big N in front, using what we discussed already in the first lecture, log of lambda minus f prime r of 1 e. And there is an absolute value here. Okay? Okay, so now what I'm going to say is that I mean, this average is complicated, but I'm going to say that this, I'm going to replace it actually by exponential of n. Integral, actually, the average, I will put it inside the exponential. And when I put inside the exponential, the only thing that fluctuates here is rho. So this is going to be d rho, average of rho of lambda, of log of lambda minus f prime r1 e. And this, you know what it is. This is the semicircle law.
Giulio, why is that justified again?
Exactly. That's the point. Why this is justified. So why this is justified? Based on what we have seen in the first lecture. So here you have rho of lambda. Rho of lambda is, well, it's a function that fluctuates. And it has a certain probability distribution, the probability distribution of rho of lambda. So do you remember in the large n limit what happened to the probability distribution of rho of lambda? Sorry? It concentrates, and it concentrates with which rate, or I mean how? It's this exponential of n was n square, right? So this means that this here, what I should do is the integral over, let's say, d rho of lambda. I mean, informally. I mean, all this is informal. I mean, to prove it, it's another thing. Of exponential of n square. Then there is a function of rho of lambda that we compute explicitly in the first lecture. And then I have plus n integral over d lambda, rho of lambda, log of lambda minus f prime of r1 So now you see, I mean, if informally you say, okay, n is large, so I can do a Laplace method or a saddle point method. Now if you do, I mean, you see, I mean, this term is overwhelming with respect to this, so this is the only one that counts. So if you look at what is the minimum of this is just given by the most, I mean, to the most probable value, which is also the average value. So this integral will be dominated by rho of lambda, which is equal to rho star of lambda, which is given by the minimum, and this doesn't count, so I can just put rho star of lambda inside here. So this is why. Yeah?
When we studied the e to m squared concentration, we threw away terms which were linear in n.
Yes. No, they are not problematic in the sense that, okay, they are there, but they don't change the fact that the rho, when you do the average over rho, the rho is the one which corresponds to the semicircle. So also this term here, they will get rho equal to rho star.
But don't they contribute to the value of the integral we compute?
No, because it's, so really here what you should think is, I mean, think to this is an average, and rho of lambda is, well, it's a probability law, and this probability is just fixed on the rho of lambda equal to rho star. So you're right, in principle there are corrections, but here I'm just saying that this average just fixed at rho equal to rho star. Okay, so now we have computed also the third term, so this term here is equal to, let me write it explicitly. It's going to be n integral over d lambda, and then here you have the semicircle law, which is 2f second of r1 minus lambda square divided by, I think it's pi fr second 1, and then you have log of lambda minus fr prime 1 e. So and this is in the exponential. Okay, so now we are done with computation for today. I just put the three terms together, and so that you have the expression, and so you see that in this way you have the computation of the complexity in this way. And then, well, you can do it, of course, in much more complicated and general case, but these are the three things in really that you have to worry about. And I would say that two things which are non-trivial, it's sometimes is this computation here. You have to understand the statistics of the random matrix that you have. And the second one is the integral over the gradient. Okay, so let's put the three steps together. And we have in such a way that we have the final expression, and then we just discuss the result. Okay, so the average of n of e. So it's going to be, for the first term, remember, was the Sn square root of n. And this is when n is large. You can compute it. It's a rather easy computation. It's n divided by 2 log of p minus n divided by 2 log of 1/2 plus n divided by 2. So this is the first term. Then you have the terms which come from the second one that computed, which was minus n divided by 2 log of p f prime r1. So this was all the normalization of the Gaussians related to the gradients. Then you have minus n e square divided by fr1. So this is what comes from, let's say, the second step. And then you have plus n, so the third step, which is integral over d lambda square root of 2 f second of r1 minus lambda square divided by pi f second r1 log of lambda minus e f Okay, should be, let me see, is f prime that yeah, I think it's correct. Okay, f1 of R1. Okay, so the important thing is here that you have an exponential of n. As I told you, we have a number of critical points that can scale with n, and then a function sigma, which is just a function of, well, the intensive energy, the energy, the big E divided by n. And so this is what is called the complexity, and you can think that this is equivalent to the entropy of critical points. Yes?
So in this case, sigma concentrates, the quenched and the annealed are the same?
So in general, no. For any f of r, no. But I will tell you in a minute in which case it concentrates. It's known to concentrate. So, I mean, it's, okay, let me see. So, I mean, sigma is what it is. It's a function. Now, what you can ask is whether quench is equal to annealed. And this is, well, this depends on the function of R1, and I will give you an example in a minute in which it does. But it doesn't have but not in general. So are there questions on the computation? So you see, I mean, this is messy, but it's, at the end, you see, you have a final expression. So for any Gaussian function on the sphere, if you know the covariance, which is, you know this function, you have an explicit expression of all the complexity or the entropy of critical points as a function of E. And now I'm going to, discuss what is the form of sigma of E, a characteristic one that you find when you study this problem. Okay, so let's go. So the first thing I'm going to discuss is the case, really this case in which still I have no signal. So still we have f of dx equal to 0. And fr of x is very simple, so it's just x to the p, which means that in the sum over, it's the energy, it has just the form of sum over I1 IP, J I1 IP, S I1 IP. Okay, just to start. So in this case, if you plot sigma as a function of small e, so here I will write it sigma A for annealed. So you find something, a curve which is like this. With here, this energy that you find here is known to be the energy of the ground state. And so in this case, for this model, it's known that indeed sigma annealed is equal to sigma quenched. So maybe here I can put some reference. So, for this problem, physicists have already, compute long ago, even before Fyodorov, so before this Katz-Rice method, this curve. And so I think the paper that did it first is Cavagna, Giardina, and Parisi. Now, the method that was used, in this case was, the method was a little bit, I would say, obscure. Even, it's not obscure, more, let's say, I would say shaky in a sense, in the sense that even for physicists that are used to replica, which is already a little bit maybe shaky, you could think, this method was more shaky. So in this case, there was no doubt that this was correct. But then when you apply to other cases, it's not so clear. So I think it's, this method, which is the Katz-Rice method, is really welcome because you know what you're doing. And then the nice thing is also that it's connected to something that you can prove. And indeed, it was, so there is this paper. Then I would say there is the Fyodorov paper, which actually was applied to something else, but it introduced the Katz-Rice. And then there is a paper that by Auffinger, Benarus, and Cerny in, I think, 2013, that he did it rigorously. So it was proven that the sigma nil is what I compute. And then actually there are two papers, one by Subag and another one by Subag and recently by Zaytouni in 21, in which they show that sigma A is equal to sigma Q rigorously. Okay, so, well, this is the curve. So what this is telling you is that indeed you have below a certain energy, of course, you don't have critical points where you have the ground state. But then when you increase the energy above the ground state, then you start to have many, many critical points. And then there was a question, well, can we distinguish what are the minima and what are saddle? And so you can redo the computation that I did, now asking to have the complexity of minima. So if you do the complexity of minima, the curve that you get is something like this. And this stop at a certain energy that in the physics literature is called threshold. And then you can do, well, the complexity of critical point with one negative, with index 1, which means a critical point that have all the direction that goes up, but one, which goes down. And then you get something which is like this. And then with sigma 2, sigma 3, etc. till sigma k, okay? So this will be sigma 1. This is the sigma of the minima. This will be sigma 2, and so on and so forth, okay? And starting from here, actually, here you don't have minima with probability 1. And you have just saddle with a finite fraction of direction which goes down. So let me just show you what are the Hessian distribution. So the Hessian distribution of eigenvalues. Hessian eigenvalues. So for the minima, what you see is that, well, at the ground state here, you have a distribution which is like this. And then when you move this way, you get something which is moving like this. And then at this point, you're right here. Okay, so this would be E ground state, and this is at E threshold. All right, and instead here, well, the critical points are typically have an Hessian which is like this, with a finite fraction of eigenvalue which are negative. So let me draw a sketch of what this is, how you should think of the energy landscape. So if you consider now the energy, and okay, it's always difficult to draw in high dimension, but let's say here you have the ground state, and what you can think is that, well, here you have just one minimum, which with all eigenvalues, the Hessian which are positive, so it's this one, which is very, very well, it's stable. And then when you go up, actually the number of minima increase, and their Hessian actually has eigenvalues which are, I mean, it becomes flatter in a sense, and then you have even more. And then at a certain point, E threshold here, they become marginally stable. I don't know how to draw a marginally stable, but then let's say when you are here, then you have things in which you have many direction which goes down and many direction which goes up. Okay, so this is the picture, caricature picture of the energy landscape, which in a certain sense is it's quite normal. No? If you think that you have a disordered system in which to find the minimum, you have to, you know that you have frustration, so you have to take it into account many different constraints. So so when you are, of course, I mean, when you are at the bottom, you will have just one solution. But more you go up, the more you can be a little bit, let's say, not so restricted with the constraint, in the sense that, well, the energy goes up, so you are not requiring to have the best possible state, so you can find several different solutions to do this. And then this will be still minima, and then at a certain point, when you go to very high energy, it's also normal that you find typically things which are critical point with several directions that goes down. Okay, see, this of course is waving, but just to give you an idea. Okay. All right, so this is for the case without the deterministic part. And now, well, I want to add the deterministic part, so we are not going to do the computation. It's easy. I mean, it's just a generalization. I want just to give you the result to see, I mean, what the competition between the random part that now you see, it's complicated, with the deterministic part is going to give you. Questions? All right, so let's consider now that you have a deterministic part. Now we add the deterministic part. The part that favors so configuration in the direction of V. So remember the deterministic part had this function f of d of qsd, and v was the signal. And so the idea is that this fd of x will be something that, well, let's say if I plot as a function of x, will be something that goes down and goes toward 1. And now there are 3 different cases that are interesting. So there is, that we are going to discuss. There is the first case, which is the case in which fd prime in 0 is different from 0. So why this is important. So what you have to think is, in high dimension, you have to think that you have a vector here, which is the vector v. And now the majority of the points on the surface lie on what we can call the equator. So they are all orthogonal to v. So the majority of the points are, let's say, around here. Okay, so well, now to understand how this landscape is done is true, and actually how easy or not is also to retrieve the signal. You have to think, how this function, that is the function that points toward the signal, is behaving in the region where you have most points. So this is why actually the behavior of this function in overlap 0, which is for when s is here, is particularly important to understand what's going on. So there is this case, f prime of d is 0 different from 0. And remember that there was the strength r, which was the strength of the deterministic part. So there was a minus r in front. And so I want to show what happens if you change r. So if r is equal to 0, well, you have no deterministic part, and you have just in this case here. So in this case, what you have, you can compute actually, I will draw it in this way. So you have, let's say, I will always put the vector v in this direction, and you can compute where are the critical points. And now the critical points are in a band here around the equator. So here you always have the v. And then if you ask what are the largest number, where is the largest number of critical points, the largest number will be here. And also, also the minimum, the global, is this one will be here, will be just orthogonal to v when r is equal to 0. Now, when you increase r, well, nothing, there is nothing very interesting happening. You know that you have this function which is different from 0. So actually, the landscape will become tilted. And so what you will see is that you will have actually, well, you will have a band actually that is reducing. So let make me reducing it. And then you have, okay, so the majority of the states that will be here. And then you will have the ground state. Let's see if I can do it this way. The ground state will be somewhere here along, okay, will be in a point like here. Okay, so this means just you have here you have a strip of critical points, and so the ground state will be here, so it will be a little bit oriented. Indeed, it starts to be oriented in direction v, and then and the largest number of critical points is here, and then this will just change, and then at a certain point, so this just gradually evolve, and then at a certain point, which is a certain rt, then everything becomes simple, and all the critical points disappear, and you have just the ground state, which is somewhere along the direction of v, close to, this is v, and there are no more critical points. Now, this transition is called, it was actually called by Jan Fyodorov the trivialization transition, which means that the landscape, so the strength of the deterministic part, which is tilting the landscape, is so strong that you destroy all the, let's say, non-convexity and complicated roughness, and the landscape becomes simple. And so here you can be sure, for example, that if you start from a random initial condition, you do gradient descent or gradient flow, you will arrive here. In this case, it's not so clear, and it's something that we're going to discuss. Okay? But so this idea that of trivialization transition is something that has been used actually has been used in physics and also in a bit in machine learning. And so this is the first case that I want to discuss. Then the second case is the case in which f prime d0 is equal to 0, but f second of d in 0 is different from 0. So this is the case in which, if you think to the deterministic part, so you don't have a first derivative, but you have a second derivative. So the landscape actually is a deterministic landscape is going down, but in a symmetric way on one side and the other, and there is no first derivative. So in this case, what you get, I try to draw it again. Okay, you have always the first thing that I'm not going to draw because it's always the same. And then you have, well, okay, maybe I will draw it anyway, up. You have the symmetric band. And then you have the majority of the states which are here. Then here, when you increase R, at a certain point, you have a second order phase transition in which, if you look at where is the ground state, so the ground state is going to be here or there. And the largest number of critical points is always here. Okay, here you have. So what I mean is that there is a region in which R is less than this critical R, in which the ground state is actually in 0 and is not oriented in the direction of V. And then if R is large enough, then the ground state will be directed in the direction of V. So here you have, this is a case in which you have a second order phase transition. And then if you continue, well, here you have, well, it continues like this. You have a band here, a band in the center. Okay. A band here, a band in the center. Sorry for the drawing. Up. And then here you have, sorry, I should say that you have a ground state here, and then you have the symmetric one. And right, and then here you have the largest number of states which are here. And then while you continue like this, and then at a certain point you will have the trivialization transition also. In which you have just one. I mean, two here. One is here, and the other one is here. Okay, so again, the landscape simplify. And then, well, then there is, if you have, well, nothing, second order, then you would expect that at a certain point you would have also the first order case. And indeed, the first order case corresponds to when you have that at second also is 0, but if the other ones are not, so let's say f, well, higher is different from 0. And in this case, well, you have something. So always the same thing here. And then at a certain point, you will have, so you have the band. And then you have actually, sorry, I should put it this way. So here you have that there is a metastable state, which is a minimum, but it's not the ground state, but it's in the direction of the signal. And then at a certain point, so here you could say, well, there is this one that appears, but it's only after that at the first order transition that this, and so the true minimum is here in this case. The true minimum will be here. And then you have a first order transition at which actually the true minimum becomes this one, but it really jumps. So here it was just a continuous way. It goes from the equator to up, and here you have a first order transition here. All right. And now it's here. And then actually here you have to go to value of R, which actually scale with n to really destroy all the minima that are here. So, well, this is just to show you that you have three very different behavior. It's interesting that you have these three behavior because then we would like to understand what's going to happen when we do dynamics. And when you do dynamics, you're always going to start on the equator, so which is the worst possible case if you look at this thing. So it's where you have a lot of minima in principle. And now you can think also about, well, you know, in physics, when you have second order phase transition, first order phase transition, you know that, well, in first order phase transition, you have this problem of metastability, which remain trapped really in a metastable state. It takes a long time to find the stable state. And you will see that indeed, I mean, this case is going to be very hard in principle compared to this one. And there is a relationship with what we know in physics. And this is something that we're going to see maybe tomorrow or in the last lecture. Okay, so this was to give you an idea of what can happen to the landscape when you have a deterministic term which compete with a random term, all the different kinds of organization that you can have. And so I would like just to conclude giving you a little bit, again, of direction in which this Katz-Rice method has been applied, and also to tell you, I mean, what things we are able to do and where is the, let's say, frontier of the thing that we are able to do, and also give you some reference. Questions? Before? No, okay. Okay, some history, reference, and what one can do. Okay, let's see if I manage to have everything here. So,
is there a way to get a full distribution of the number of critical points, not just the mean?
yes, so in the case of, I mean, in very specific case, so in the case with no deterministic term, yes, in that case you can get it, you can get, okay, let me see, maybe I said yes too quickly. So in this case, I think you might be able to get the all the moments, but the distribution, no, I'm not sure. Don't think so. Okay, just for the history and some reference, maybe I should also say that something that I didn't say, so that this case here is the case which corresponds to tensor PCA. And in this case, so the annealed computation was done in a paper by, so it was Andrea with, so Benarus, May, Montanari, and Mika in 2019. And then there was actually a computation that we did in which we did the quench computation with replica. So it's not rigorous, this is rigorous. But we got the quench result, which was Benarus, myself, Valentina Ross first, Benarus, myself, and Camarota. 2019 also. And then there are actually generalization of this in which you consider a tensor PCA and matrix PCA that was done by Stefano Sarao and, well, many of us. So Lenka, Florent, myself, Per Francesco Urbani, Chiara Camarota, and I hope I'm not forgetting anybody. Okay, so, well, the history, so it's the history of computation of critical points. So as I told you, first there is a lot of things done in spin glasses, but with methods which are completely different and which I would say are shaky, even for, let's say, theoretical physicists. And then, well, the Katz-Rice method now is used, even if you don't care because you are interested in machine learning, is really used in a lot of different problems, not just in physics, but in physics. And then, well, also in, well, other things, and even you would be surprised in things like ecology, in which you want to have the number of equilibria, for example, of a big ecosystem. In the case of, so as I told you, the annealed computation these are rigorous. And actually, if you want to see, I think there is a recent review that I don't have here, but I think it's by Aufinger, Montanari and Subag, right? In which there is 1/3 of it, I think, which is about this. So it's really 2022. And then non-rigorously, what we can do indeed, we can do the quenched is done with the Katz-Rice method plus replica. And the paper in which was done is the one that I described before, Valentina Ross and others. Now, in the case of neural network, and here I'm afraid I have to erase something. Okay, in the case of neural networks, actually there are interesting computations that have been done for recurrent neural networks. So these are models that were, I think, studied at the very beginning by Imson Polinsky. I don't think he will discuss this, but and you can study actually the number of equilibria in this case, and this was done by Wainwright, Tugul, always with this method, in 2013. Now, in neural networks, so in estimation problems, for example, with the Interson PCA was done in this paper. So in neural network is really a little bit the, let's say, the frontier of what we can do. And you can already see why it's difficult, because the loss landscape of a neural network, even simple one, is not Gaussian. And all the computations that have been done, the majority of them are always this landscape is Gaussian. Now, what we did recently, which is, I think, it's really the frontier in this sense, if you consider a loss function for a teacher-student network, which is defined in this way, which I think has been defined already. So you have a certain loss, which depends on, let's say, the overlap between the data and a certain teacher. And then you have xi mu dot w, so it's a teacher-student network. So here you see, in this case, and xi mu are Gaussian variable. So in this case, the loss is clearly non-Gaussian. And in this case, you can actually do the Katz-Rice computation in an almost rigorous way. And this is what we did with Antoine Maillard, Gérard Belarus, and myself. Which was, I think, 2019. So just to say that we are at the level at which we can indeed start to study problems like this, which are, well, it's the simplest case in which you have, well, I mean, we can do it with one node, we can do it also with more nodes, with the teacher and the student, and compute the landscape. Now, if you ask me, how is the landscape? That's a good question, because it was, we arrived at the end, we got the equation, and then the question is still there. We didn't study them, but in principle, it's not. I mean, they are not so complicated. It's just that you do a very big thing, and then you say okay, and yes, just a moment. And so, just to say that in principle, I think it's now the method can be applied to simple case with a few nodes, teacher and few nodes students, and so hopefully, well, since you are here, and if you want, I mean, if you have an example like this in your head, and you want to know how is the landscape, you can take the equation that we have or generalize them a little bit and then study the landscape in your simple neural network. Yes?
My question was about the RNN, because I have the RNN in mind for discrete variables.
No,
This method is applied to continuous.
yes, it was continuous variable. It's a simple
version of RNN.
Yes, it's a very simple continuous version of RNN. Yes, in which you have yeah.
What's the energy function for RNN?
Let's see if I remember it. I think, okay, not sure I remember correctly. So it was something like x dot I, which was equal to minus lambda xi plus, maybe Remy can help me, gij, and then here there was there is a plus g here, and then maybe an hyperbolic tangent here. J. So these were the equation?
Yes.
Okay, it's not Remy that helped me, but somebody else. Okay, thank you. So these are the kinds of dynamical equations that you have. And indeed, so this equation have, well, in principle, have a lot of equilibria. And depending on G, so if G is small, you have just one equilibrium. And then when you increase G, at a certain point, it's known that this system starts to have a chaotic phase in which dynamics is chaotic. And this is exactly at the point at which you start to have a lot of equilibria, and all these equilibrium are actually unstable. So you have an explosion of unstable equilibria, and this coincides with where these systems start to have chaotic dynamics. Other questions?
Do you have isolated critical points in your case, in this teacher-student setup, or do you have like manifolds of minimum critical points and things? And do you...
So now here they are isolated because otherwise, I mean everything. So it's everything diverge. So you cannot have lines of critical points when we do this computation. Otherwise, we will get infinity. So this indeed is a limitation of this method if you want to try to apply this method to an overparameterized regime in which you have a manifold of, for example, zero energy configuration. This is really wouldn't be useful. But now if you think, for example, to what Nati have said, so that you should think that the gradient brings you in region, that maybe you could find statically, I mean, with a just static computation in which you put some regularization. So you could think that you study a loss function plus regularization in which you have minima that are really separated, and then you can do this computation. So this computation, if you have a line or manifolds of critical points, will give you infinity. Other questions? Okay, so what we are going to do tomorrow is that we are going to now, you have all this landscape. Now you can think what's going to happen if you do dynamics, so if you start from a random initial condition. Is the system, do you need to wait for the trivialization transition? So you need to wait that the landscape becomes completely convex to find the minimum. Or you can also find the minimum when you have an exponential number of bad minima which are around. So this is the kind of question that we want to address. And when is it possible? When is not possible? So in order to do this, again, I mean, it's my spirit in this series of lectures also to teach you methods. So I'm going to teach you a method that allows you to study the dynamics of this model. So the ones that I described here, which is, let's say, more estimation, and the ones that I described here. And this model is called dynamical mean field theory. It comes from physics. So I will teach you first the method, and then we will tell you what are the results. And so this will conclude my series of lectures. So thank you.